Hello, this is Dr. Coroner, and this is the pre-lecture video for Chapter 1, Part 2. Today we'll be talking about units, significant figures, and dimensional analysis. When dealing with units in science, often we use the SI system. This would be the meter, defining the length scale, mass is the kilogram, temperature, Kelvin, time, seconds, amount of substance, the mole. We get into moles in Chapter 3. We'll talk about Kelvin a little bit later in this lecture today if you're not familiar with that temperature scale. Electrical current and luminous intensity, these are not units we encounter a lot in Chem 1210, but those would be the amp and the candela. One of the important things here is that these are the only 7 base units in the SI system. Any other SI unit, like for example a liter, that unit is going to be derived off of one of these fundamental units. And of course we could have other non-SI units that we encounter frequently, like pounds or ounces. Those units have conversion factors to and from the SI system, and we'll talk about converting units using dimensional analysis towards the end of today. When working with the SI system, we often will use metric prefixes in front of the units when convenient. So we have units such as petawatt, terawatt, gigawatt, megawatt, kilowatt. These are for dealing with large measures of watts. So say we have 1,000 watts. Well, we could call that 1 kilowatt. Or say we have 2 million watts. We could also then just say, well, that's 2 megawatts. Say we have 9 billion watts. We could call it 9 gigawatts, and etc. We can also encounter units that are on the smaller side. So if we have a small measure of a unit, then maybe we're going to use a unit like milli, micro, nano, pico, etc. And so 10 to the minus 3 would be milli, 10 to the minus 6 would be micro with the unit mu, the Greek letter. Nano would be 10 to the minus 9. And so one of the key things here that I like to point out is that we could define our conversion factors 2 different ways. We could say 1 nanometer is, we see nano is 10 to the minus 9, so that's 10 to the minus 9 meters. And of course we can divide both sides by 10 to the minus 9, so we can figure out how many nanometers there would be in 1 meter. So 1 meter would be equal to a large number of nanometers, 10 to the 9. So anytime we have a conversion factor, we really have 2 conversion factors, because you can say, well, how many meters are in 1 nanometer, or how many nanometers are in 1 meter. So a large number of nanometers in 1 meter, and a small amount of meters in 1 nanometer. That's why the nanometer is relating to a small quantity. Now what I want to point out are the units that I would expect you to know, or the prefixes I would expect you to be able to use without us defining them. And so I'm just going to square this box here, that these are going to be the ones that we frequently use in this class without defining them, say on exams or quizzes and things of that nature. So moving on, volume is one of these non-SI units I mentioned earlier. It is a derived SI unit, and it's derived off of the unit from length, because volume, of course, is length times width times height. So if you go 1 meter times 1 meter times 1 meter for defining a box, that would be a decameter. That would be a really large volume. And then, the square box would be 1 cubic meter. So 1 cubic meter would be a large volume. Now how that would relate to the liter is by the conversion, that 1 liter is 1/1000th of a cubic meter. So there would be 1,000 liters in 1 cubic meter. So go 1 meter by 1 meter by 1 meter, that's 1,000 liters. Now another common unit is a cubic centimeter, again off a length scale, 1 centimeter by 1 centimeter by 1 centimeter. That's the definition of 1 milliliter. So a milliliter is exactly equal to 1 cubic centimeter. Now we have lots of different glassware in the lab that we use for measuring volumes, and we have different types of tools for different sorts of scenarios. So we see a graduated cylinder. Now a graduated cylinder, this device here is good for when we're trying to add volumes with about plus or minus 1 milliliter of precision. So if we're trying to add 25 milliliters of liquid to a solution, and it doesn't matter if it's 24.5 or 25.5 milliliters, then a graduated cylinder might be a good tool. Now if you want to go about plus or minus 1 milliliter, then a syringe is a pretty good tool. So with a 0.1 milliliter of precision, you could add, say, 12.5 or 12.6 milliliters to a solution. Probably not much accuracy or precision in between this unit here. Now a burette gets you about plus or minus 0.01 milliliter of precision. Now the way a burette would work is you would fill the burette, note the volume before, let some of the liquid drain out, and then take the difference. And so by difference you could get a very precise measure of the volume that was delivered. Now a pipette is good also to about plus or minus 0.01 milliliters of precision. Now a pipette would work by having a bulb, and depending on the size of the bulb, it would have a number on it, like a 5 or a 10 or a 25, and then it would have a little marking on it. Now the way the pipette would work is you would take a beaker of your liquid, put the pipette into the liquid, make sure the pipette's not resting on the bottom of the beaker so that there's enough room for the liquid to be drawn into the pipette when you squeeze the bulb. So squeeze the bulb, put it on the pipette, hold your pipette in the liquid and let the bulb go, or let it suck the liquid up into the pipette, let it go and the liquid rise above your notch on your pipette, and then at that point take your pipette, rest it on the beaker so that you can gingerly or quickly put your finger on top of the pipette so that the volume doesn't drop below your notch. And then very slowly and carefully let the volume lower just until you get that meniscus resting on the notch on your pipette. So then if you have, say, a 10 marked pipette, then you know you're delivering 10.00 milliliters. If you then very quickly and carefully take just the contents of the pipette, like get rid of the last drop hanging off, and then put that into your container and drain it in. And then the last thing you do with a pipette is you don't force that last drop out with the bulb. So you very routinely use a pipette in a very similar fashion, then you get a very precise and accurate delivery of liquid with that device. And so we see different types of glassware here designed to deliver different levels of accuracy and precision of liquids. So you get a very precise volume with a pipette. You don't exactly get a precise volume with a burette. So if you want to add 10.00 mils with a burette, that's going to be pretty hard, though you can probably deliver 9.98 milliliters versus 10.04 milliliters and accurately know the volume, just not precisely on the target you want. Lastly, a volumetric flask has also a notch and usually a size, say a 25 mil volumetric flask. You fill this flask to the meniscus line here, and then you know that flask contains 25.00 milliliters. So also about 0.01 milliliter of precision with the volumetric flask. So those are some common tools for measuring volumes in the laboratory. Temperature is does have a base SI unit of Kelvin. The Kelvin scale is our temperature in Celsius plus 273.15. Now the interesting thing with the Kelvin scale, or the interesting thing about temperature before we get into the different scales, would be that temperature is related to the heat of an object, and then heat flows spontaneously from the hot object that has more energy to the cooler object that has lower energy. So one way to think of this is imagine a molecule is vibrating and rotating very quickly. It can then bump into other molecules, transfer that energy to the other molecules, so they become rotationally and vibrationally more excited or energetic molecules. So our heat's always flowing from the hotter to the cooler object. Now our Kelvin scale, as we mentioned, 273.15 added on to the Celsius temperature. Now what this is setting is the lowest temperature an object can have is 0 Kelvin. And so 0 Kelvin would be minus 273.15 degrees C. So the lowest temperature any object could have would be minus 273.15 degrees C. So if you add 273.15 Kelvin to that, you get 0 Kelvin. So Kelvin at least sets our 0 point, our lowest possible energy, our lowest possible temperature that an object can have. Now our conversions to and from Fahrenheit would be our Fahrenheit temperature would be 9/5 the Celsius temperature plus 32, and then likewise the Celsius temperature would be the quantity of the Fahrenheit temperature minus 32 times 5/9. And so what might be useful real quick would be to go through room temperature, 25 degrees C within our different scales. So 25 degrees C, what is that in Fahrenheit? Well, we would plug in 25 times 9/5 plus 32 that would work out to be 77 degrees Fahrenheit. And then we could also add 273.15 to this, and that comes out to 298 Kelvin. So 298 Kelvin, 77 degrees Fahrenheit, 25 degrees C, all the same temperature measurement. Now, one final thing to point out with temperature is our different scales. So look at Celsius versus Kelvin. So if you go from the melting to the boiling of water, so water, of course, melts at 0, boils at 100 degrees C, add 273.15, so it's 273 to 373. So it's 100 units of Celsius difference for the scale in Celsius, and it's also 100 difference in units in the Kelvin scale. And so what that means is our delta T is the same in these two scales. So like if an object increases its temperature by a Kelvin, it's also increased its temperature by 1 degree C. Now that's not true with the Fahrenheit scale. And so with the Fahrenheit scale, we see the boiling of waters at 212, melting's at 32. The difference is not 100 units. It's a lot more units. It's almost double. It's almost 200 units. And so that's not the case for the Fahrenheit scale. Okay, so the Fahrenheit scale does not have the same difference in temperature as the Celsius and the Kelvin scale. So the energy is another one of the quantities that does not have a fundamental SI unit. Rather, it has a derived SI unit, and this one would be the joule. So if you think of kinetic energy as 1/2 mv squared, and then think about the units you might plug into this equation to get SI units out for each of the quantities. For mass, you would plug in kilogram. For velocity, length per time, you'd plug in meter per second. Those are our fundamental SI units for those quantities, and then square the velocity. And so this is going to be the derivation of that unit for our joule. So 1 joule turns out to be equal to 1 kilogram meter squared per second squared. Now the calorie is a non-SI unit. Now it's commonly used. The calorie is actually defined as the amount of heat it takes to raise the temperature of 1 gram of water by 1 Kelvin or 1 degree C. And so that works out to be in joules 4.184 joules. Now this is an exact conversion. And I point that out so that you don't think or wonder, is that 4.184 rounded off of some larger conversion factor? No, that's the exact conversion factor. Now this calorie is not the nutritional calorie. So if you look at a food item, if you're looking at a granola bar that says it's 100 calories, that's 100 capital C calories, meaning it's really 100 kilocalories. So that'll give you 100 kilocalories of energy in order to do work with or heat your body up with. So a nutritional calorie is a capital C calorie. It's also 1,000 calories or a kilocalorie. This is often why if you see people on nutritional websites talking about their diets, maybe they list their intakes in units of kcals. Density is another physical property that does not have a fundamental SI unit. It has a couple of different units we commonly use. Grams per milliliter or centimeter cubed are common. We can look at some different types of substances and compare their densities, because density turns out to be one of those intensive properties of a substance, a characteristic property. So air is not very dense. Wood as well, not very dense. Water, 1 gram per cubic centimeter. Ethanol, a little bit less dense than water. And then table sugar, table salt, a little bit more dense. Iron and gold are so-called heavy metals. They are much more dense, have more mass per unit volume compared to other substances. Now let's begin to get into dealing with calculations and numbers and calculations, which will be sort of very common with a lot of different topics we get into in Chem 1210. And so let's begin in kind of a strange place to maybe, you may not expect that this is where we would begin, but let's talk about exact numbers versus inexact numbers. Okay, so if you could count something very carefully, if it's a small quantity like 12 eggs, you know if you have a dozen eggs, if there's 12 of them present, you can very easily count them. And so if you're going to say I have, 2 dozen eggs, it's like, oh, I exactly have 24 eggs. It's not like you're wondering, do I have like 10 or 20? Is there some, measurement that's being done here? No, it's a very exact and easy to determine number. Now, there's inexact quantities, and these are really what we encounter most frequently in science, because these are the things that we're reading off scientific instruments. Because we're going to see that all of our instruments that we use have some type of error associated with them, and then there's also human error involved in using these instruments as well. So there's kind of two different types of errors we're going to have to worry about. One is just the sort of normal noise you get with a particular quantity, and another is the inexact nature of humans entering the equation. So anytime we're taking measurements in the lab or encountering numbers with units where we're imagining that these are laboratory defined or measured quantities, that these are inexact quantities. So now let's think a little bit about how we might talk about uncertainty in our measurements. So say we're trying to determine temperature and we are using probably not a very good thermometer. Let's say it only has a notch at 25 and a notch at 30. And so here we have some temperature reading in the middle, definitely not 25, definitely not 30. But if we're going to say this is 26 or 27, we might have to either make our own markings or start arguing with each other. And so maybe we could settle on 27, and maybe we could all agree that 27 plus or minus a degree is about as good as we can say with this particular tool. Now, if we were to have a better tool, maybe that would be one that adds some markings and even some finer markings as well. If we had such a device, maybe then we could say it's 26.8 degrees C and not 27 plus or minus 1 degree C. So with whatever tool it is that we're using, we're kind of limited by that tool to determine the quantity it is that we're measuring. The very last digit is usually the one that we're going to argue about. It's still significant, but it's not exactly exact. So we're looking at the 27 here before I started marking this page up. We weren't too sure if that was 26 or 27, or we could probably say it's not 28. So we're probably arguing if it's 26 or 27. So we're not really certain in that last digit. So we're still arguing. So it's not exact, but it's still significant. It's still significant of a number. So we look at 27 degrees C and we'd say that's a value that has two significant figures. Now, if we look at 12 eggs that we counted, we look at this and say, well, that's infinite in terms of the number of significant figures. So this would be an infinite number of significant figures. And we only know that because we counted them. We know with our eyes there's exactly 12 eggs present. Now this is going to play a big role. If you start saying, okay, take two different quantities, one is exact, another is inexact, and you start doing math with them, we're going to run into some issues. Okay, so let's talk a little bit about accuracy versus precision. Precision is a measure of how closely individual measurements agree with one another, and accuracy refers to how closely individual measurements agree with the correct or true value. And so if we look at the top bracket here, we see that we have 3 darts all on our target. So because they're on target, that means we have good accuracy. Because they're all together, we have good precision. This is a perfect scenario. So this is what we hope to find in the laboratory. We have good instruments and we have good use of those instruments. Now if we go to the lab and we find 3 targets that are all together, that means we had good precision, but they're not on the target, so we had poor accuracy. Now what this would mean is this would be a calibration issue. Or there's something wrong with one of our instruments that we're using. Probably not a human error though. We're using the instrument correctly. That's why they're all together. That's why we have good precision. So then if we go in a lab and find, well, we're not on target, we are missing our target, and none of our measurements are together, this is probably meaning maybe we're not doing the experiment correctly. So this would suggest, well, why don't we refine our skills as scientists and go back in and try the experiment again, maybe also then try to fine-tune the calibration at the same time. So kind of fix our skills, fix the instruments, and go and try again. Okay, and so what this is kind of getting at is just one, it's possible in the laboratory that we can have any one of these 3 scenarios play out. This is often why in the laboratory we'll try to take 2 or 3 determinations of the same quantity so we can get a good understanding of, is it us? Is it the equipment? What's going on behind the experiment? Usually you can get a good understanding by comparing your results across a couple of different trials. So now significant figures come up in calculations because all digits of a measured quantity, so this is dealing with our inexact numbers, we have to start counting or looking at the digits as being significant when they're given within a unit. And if there's digits not in the quantity, they're insignificant. Like for example, if we see a mass of 1.23 grams, that's 3 digits of precision. That's different than if we said 1.2300 grams. This implies a higher level of precision. So this is a higher degree of precision than this quantity of 1.23 grams. Okay, so when rounding calculated numbers, we have to pay attention to significant figures so we don't overstate the accuracy of our answers. So we have to be really careful not to overstate how accurately we know a quantity. And I'm sure you can appreciate that when you put calculations into a calculator, usually you get the whole calculator filled up with numbers. Well, we have to know where to round our result to. And so maybe in the past or early stages of high school or middle school work, your teacher would just say, well, give me 3 digits. And some of the cases, it'll just be 3 digits. But we want to very carefully use some rules of statistics or significant figures to know precisely where we should round our. So significant figures, let's talk about what makes a quantity significant versus insignificant. So all non-zero digits are significant in a quantity. The zeros between non-zero digits are significant. Zeros at the beginning of a number are never significant. We'll talk about that in a moment. And zeros at the end of a number are significant if there's a decimal point involved, if the zeros come after a decimal point. So let's look at a couple examples here. We see 1.03 times 10 to the 4 grams. That's signifying 3 significant figures because I see 3 digits here. So 1, 2, 3, there's our 3 significant digits. Throw on a 0 after the 3, that's signifying the quantity with 4 significant figures. Add another 0, that's 5 significant figures. Now, if I had a unit that was, say, 11,500 grams, how do you know if that's meant to be 1, 2, 3 sig figs, 4 sig figs, 5 sig figs, or even more sig figs? Well, what I would do is I would call this 3 sig figs. And if I wanted to signify the quantity with even more precision, then I would have to use scientific notation. So if I want to express this with 4 sig figs, then what I would want to do is call that 1.150 times 10 to the 1, 2, 3, 4 grams. Okay, so see what I did here is I went to scientific notation, so I'd be forced to write in a 0. So if I want to express this quantity with 4 sig figs, I need to use scientific notation to do that. So without scientific notation, I'm just assuming that only the non-zero digits are significant, and then I'm not counting the zeros as being significant in the quantity. So let's start moving towards doing some calculations and knowing how to round our results. So the least certain measurement limits the number of significant figures in the answer. And so when adding or subtracting, the answers are rounded to the least significant decimal place. When multiplying or dividing, the answer is going to be rounded to the same number of significant digits as the measurement with the fewest number of significant figures. Now, one of the keys here is that this is dealing with math of inexact quantities. These are not quantities we count or numbers we know exactly. These are only for dealing with the issues of inexact or measured quantities. And so then lastly, when we do multi-step calculations, we're going to track the digits throughout the problem and then round off only at the end of the problem. And we'll give some examples of this as we go along. So let's look here at a couple of examples to go through our different rules. We have 75 meters plus 75 meters. Now we plugged it into a calculator, it says 150. I always implore you, we're not changing arithmetic. It's just a matter of how do we round or report these quantities once we do our calculations. So we get 150 in our calculator. You may look at that and say, well, you said earlier that only the first 2 digits, only the non-zero digits are significant. Well, that would be true if I just wrote 150 meters. If I just wrote 150 meters and said how many sig figs, that would be 2. This is a different problem. We're saying take 75 meters plus 75 meters, how many sig figs do we have? Now, one of the keys I want us to think about is how 75 meters, it's like plus or minus a meter, is what that unit means. As opposed to if we had 75.0 meters, that would be 75.0 plus or minus a tenth of a meter. So if we have 74 to 76 meters and we add 74 to 76 meters to that, we have about 148 to 152 meters. Do you see how our wandering, our uncertainty is in that 0 digit? Significant, but not certain. Okay, so we report this value as 150 with 3 significant figures. Now, how do we do that? Well, what we would do is use scientific notation to do this unambiguously. So we go 1.50 times 10 to the 2 meters. Okay, so clearly I've written 3 digits. The 0 is significant because it's to the right of a decimal place, and our quantity is clearly expressed now with 3 significant figures. Now what if we flip that plus sign around and just do 75 times 75 meters? Okay, now again, it's kind of like the idea is plus or minus 1 meter, plus or minus 1 meter. Now, our result would work out to be 5625 meters. And so for 5625, for our answer here, how many of those digits, now the unit's square meters, how many of those digits are significant? Well, if we go back to our rule says for adding and subtracting, we look at our placeholder, we round to the same placeholder as the value with the lesser placeholder. Here they're the same decimal place, so we round to that one's placeholder. When we multiply and divide, it's about the quantity with the fewer significant figures. Both of them have 2 sig figs. So 2 sig figs times 2 sig figs leads us to a result that is good to 2 significant figures. So we should round to that second significant figure spot for 5,600 square meters. So we report this as 5,600 square meters. Now that's fine, there's nothing wrong with reporting it that way. Or we could also write this as 5.6 times 10 to the 3 meters squared, if we want to be extra clear. So either way is fine here for that quantity. We really do need to use a scientific notation though for our first problem. Okay, now I want to go through one other example with the addition rule and then do a multi-step problem after that. So if we look at our problem here, what I want to do is set the stage for why it is we might have this problem. Maybe we use a balance that's good to 4 decimal places. You'll use one in the labs called an analytical balance. It's a very precise balance. So let's say we put an object on there, we figure out its mass is 1.2345 grams. Let's say we add that to another mass that we measured out to be 75.57, though on a different balance. It's only good to the second decimal place. You see how we're kind of like losing the amount of precision we had gained with our new tool by using or adding this mass to a lesser defined quantity. So when we do our arithmetic here, this would work out to be 4508, so 76.8045. And so our result here is only going to be good to the quantity at the less significant decimal placeholder, which is this placeholder here. So we're going to drop the 45, round to the, I usually call it the greater quantity placeholder, or the greater quantity decimal place. That's where we round our result here. So we end up with 4 significant figures when we finish our problem here for this example. And then lastly, we have, maybe we're trying to determine the density of an object. So we have the mass of some object is 5.23 grams. Maybe what we did was we put this object into a graduated cylinder. So we maybe had a graduated cylinder, then we throw the object into the cylinder, the volume increases, and then we take the volume before minus the volume, or the volume after minus the volume before to get the volume of the object by displacement. So what we're going to show here is multi-step how this problem works. So 21.8 minus 17.5. So if I do this problem here, 0.3, and so 4.3 milliliters is the volume. That only has 2 significant figures. 2 sig figs because I have 3 minus 3, but they're both to the same placeholder, so I report that to the tenths placeholder. So I have 2 significant figures. I divide that into 3, so I go 5.23 divide by 4.3. That works out to be 1.216 on my calculator. Even more digits are shown. But that's only going to be good to the second significant figure because I have 2 sig figs going into the 3, so that's only going to be good to 1.2. And then the units here are grams per milliliter. Okay, so when I do multi-step calculations, I just do and apply the rule sequentially as I'm doing the calculation. So I have to do the subtraction first, so I apply that rule go to two significant figures, divide it into the quantity with 3. When I multiply and divide, it's about counting sig figs. I see 2 sig figs divided by 3, so the quantity is only good to 2 significant figures. Now notice here, you can't just look at the problem and say, well, 3, 3, 3, the answer should have 3. It doesn't work out that way. We have to plug in and do our rules each step of the way. So hopefully these examples give you a good idea of how to apply these significant figure rules. So our final topic for today is dimensional analysis. So dimensional analysis is used to change units. We can use conversion factors like 1 inch to 2.54 centimeters as an equality. And we can set up equalities. Like, of course, you probably remember trying to figure out, say, how many seconds are in a day. So you do number of seconds will be 1 day. Use a conversion 1 day to 24 hours, 1 hour, 60 minutes, 1 minute, 60 seconds. So it's all about getting towards that unit you're looking for and then canceling out the units as you go along until you get to your desired unit. And so I'm sure you all remember how to do problems of this nature. Now, the thing with dimensional analysis is we'll use it to problem solve in this class, not necessarily just to convert units. So let's look at an example in the next slide of a problem just like that. So here is a sample problem. We see what is the volume of 2.50 kilograms of pure ethanol with a density given, but in liters. So what we want to know here is the volume in liters of this quantity of liquid. So we have 2.50 kilograms of ethanol, but we see the densities in grams per milliliter. So what I'm going to do is convert to grams. 1 kilogram is 1,000 grams. Written very poorly, so 1,000 grams. Now we see our density is 0.7893 grams per milliliter, and then 1,000 milliliters is 1 liter. Okay, so I'll leave the calculation for later, but that's how we would set up this particular problem. So let's talk about the exact versus inexact nature of quantities by going through a couple of different types of quantities and thinking if we could ever know exactly these quantities. Okay, so for example, the number of people currently in Ohio. So the issue here is not so much if this is a quantity that ever exists. You know, for like a moment in time, if you take this very second right now, there have to be an exact number of people in Ohio. But the question is, can we determine it? Can we ever really truly know what that is? The degree of precision it would take to count every head at one given second, where we know every second we have people entering and leaving the state on the highways. We have people that are being born, people that are dying, maybe not every second, but it happens. So that's going to be almost impossible to track in a given moment to take a snapshot of how many people are in the current state. So this value here, we would say this is inexact. We'd have to make an estimate if we want to know how many people are in Ohio right now. So that would be an inexact quantity. Number of students who attend your first lab session. You could exactly know that quantity. It's probably going to be 25, maybe 24, but you could clearly count the number of heads in your first lab session. So this is something we can know exactly. Number of atoms in a bottle of water. Again, there is some number of atoms in that bottle of water. Now, if you have it sealed, maybe you could agree that it's mostly constant throughout time, that the water isn't leaving or being added to the container. So the atom count would be constant, but could you ever count that high and determine it that precisely? So the answer would be no way. That would be something you'd have to measure or estimate. Amount of currency in the world. At any given moment, it's changing because the currency rates, different, currency are always changing anyways. But you could never count up all the money in circulation at any given moment because this is a quantity that's always changing and it's something that's very, very large. So again, we'd have to estimate that quantity or take a measurement of it. Lastly, the amount of money in your checking account. That's something you could probably look up very accurately right now if you wanted to. So that's something that you could usually know very exactly. Okay, so the issue here, and the thing I really want to highlight here, is a lot of these quantities, you can imagine there being a number. you can imagine maybe there is, at some moment, a total amount of currency in the world. It's just your ability to know what it is going to be very, very limited. So the way you would ever go about determining that quantity would be through a set of measurements, which is going to lead into using rules of significant figures along the way. Lastly, some further sample exercises using sig figs. I figure maybe you want to see a few more examples. 55 plus 55 says 110 on your calculator, but 1 plus 1 would lead the answer to be good out to that last placeholder. So 3 significant figures, 1.10 times 10 to the 2 meters. 5.5 times 5.5, that's going to be 3,025 on the calculator, but only good to 2 significant figures. So 3,000 square meters. You can use an underline in your notes is good enough, but if you want to express this, say in a lab report more precisely, be 3.0 times 10 to the 3 square meters. 55 divided by 55 grams divided by milliliters says 1 on your calculator, or just, without needing a calculator, that's 1, but we have to pick up a decimal place, 1.0 gram per milliliter, because 2 sig figs divided by 2 sig figs is good to 2 significant figures. 55 plus 8.5 times 8.5, I'm going to throw that onto a calculator. 8.5 times 8.5. That's going to be good to 2 significant figures. That's 72.25. And I'm going to add 55 to that. Now, let me come back here and say that 72.25, that's only good to 2 significant figures. When we multiply, we count significant figures. So that's 72. Add that to 55. We get 127. 127, good to that ones placeholder. We have a ones placeholder plus a ones placeholder, so we're good to the sevens placeholder in that value there. So 127 square meters. Convert 25.75 inches to centimeters. Okay, number of centimeters. 25.75 inches, 1 inch is 2.54 centimeters. Now this is a hidden significant figure problem. So 25.75 times 2.54, a lot of times this is an exam problem. That's 65.405 on my calculator. Is that good to 3 or 4 significant figures? You may look and say, well, that's 3 sig figs times 4 should be 3. And you got to remember, 2.54 centimeters is exactly the number of centimeters in 1 inch. Both of these quantities here are exactly defined. They have infinite numbers of significant figures. If you want to round this to 3 sig figs, I would say, why don't you round it to 1? You say 1 inch. Why wouldn't you round it to 1's placeholder because of the 1 and the 1 inch? Well, the answer is because it's exactly 1 inch, has exactly 2.54 centimeters. We got to keep all of our placeholders here that we start with. So we start with 4 decimal places. We're going to end with 4 decimal places. So we go 65.40 centimeters. Now there is a weird rule in the book about rounding to an even digit whenever you're exactly at a 5. We can talk about that later. It's really not that big of a deal. So yeah, you can read about that in the textbook if you're interested. Now lastly, I want to do a cubic conversion, just to highlight doing a liter to cubic feet conversion. How do we do this problem here? So if we want to do the number of feet cubed, I like to start my dimensional analysis with the unit I'm looking for, so I clearly know where it is I'm trying to end up. And I'm starting with 7,500 liters. Okay, now what I'm going to try to do is use the units I know. I'm not going to try to look anything up here. And for most of these problems, you're not going to get much info on your exam, so you should probably try to do these conversions with just using the information you already know. So 1 liter, we saw earlier, does it help me to go to 1,000 milliliters? Well, maybe, because I know 1 milliliter is a cubic centimeter. And I know a centimeter to an inch conversion. So I know there's 2.54 centimeters in an inch. Now, how does that help me here? Well, I can cube the whole conversion. So if I go 1 inch by 1 inch by 1 inch, that's going to be equal to 2.54 centimeters by 2.54 centimeters by 2.54 centimeters. So that's 1 cubed inch cubed equal to 2.54 cubed centimeters cubed. So meaning I start with the inch to centimeter conversion, and then I just cube the conversion. So I take the conversion I know, 1 inch is 2.54 centimeters, and I cube the whole thing. So I cube the 1, cube the inch, cube the 2.54, cube the centimeters. And then all I need to do is do the final 12 inches. And I will say that I understand international students probably wouldn't know the inch to feet conversion and the inch to centimeter conversions as maybe automatically as domestic students. So we would probably give the centimeter to inch, the inch to foot conversions if we were to put this on an exam. So if you're sitting there thinking, I've never even heard of a foot before, because this is your third day in the United States, we would give you those conversions on a test. But the point here is we wouldn't give you the cubic inch to cubic centimeter conversion or the cubic feet to cubic inch conversion. You'd have to work those out and then apply them within the problem to work it out. So I'll let the answer go. I'll just leave it here worked out. So if you throw this into a calculator, you could figure out the number of cubic feet in 7,500 liters. Okay, so that's the end of our pre-lecture video for today. I hope this is on the longer length of pre-lecture videos. The sig fig rules are hard to explain. You have to do a lot of examples. You have to do a lot of practice problems. It seems really easy. It's just counting and arithmetic. It's really, really basic. So at first glance, it seems so simple, but the rules are complicated to understand how they're applied. So I think doing a lot of examples, hearing a lot of examples will be helpful along the way. So hopefully you found this video helpful, and we're ready to go look at more examples in lecture soon. Okay, thank you for listening.